Hello, everybody. I'd like to welcome you to my YouTube channel. This is Steve with C64 Brain coming back with, believe it or not, video 10, and we're going to even embed 11 in this video. So I've been away for a while. I realize that, and I appreciate your patience as game design and life experiences kind of get in the way sometimes. If you're new to my channel, feel free to go ahead and subscribe. I appreciate that, and ring the notification bells. For this video series with Project 10, we will be learning how to implement a character set into our program by exporting files saved in ChartPad and then use our program to pixel scroll through the bits to achieve an interesting type of animation. I forgot to mention that if we have time, we will also explore Project 11 involving the hex character set display of game parameters and position of text messages on the screen display. As mentioned in the previous video, the maps for the Commodore 64 game project were designed with a Windows tool known as ChartPad. This tool allows you to create a map in real time or load one into the editor. After the map is complete, you can then save the map files known as exporting and the character sets and the tile sets, and that can be used in your own projects, which we'll see in a demonstration. Characters in memory. To understand character animation, it's important to learn about the character set. Characters are stored in an area of big memory known as character ROM. This standard character set exists between D000, which is 53248 from the big chip, all the way through DFFF, which is known as ROM memory, of course. A close examination of some keywords reveals these characters underneath the keys as seen in this picture. So I'm showing a picture of the Commodore 64 keyboard just so you can kind of get a perspective of what I'm talking about. If you're using Vice C64, you may not be able to see this, but you can go ahead and Google if this example isn't clear enough. But underneath the characters themselves is actually this little display. They had on many keyboards we could actually see the actual AXI or PET-AXI characters that would be used in an actual character set after you copy over from ROM into RAM memory. So these are arranged in a set of dots. We can also call them pixels. Each individual character you see on the screen is contained in a dot matrix calculated as 8 by 8, 64 total pixels known as bits. These individual bits are turned on in an arranged pattern to generate characters on the screen. For example, if you type a letter or graphical character, it's made up of bits. And as you look here, you'll see this is an example I have of an actual individual 8 by 8 character. And you can also see the bytes on it. And if you look above there where it shows 128 all the way down to 1, those are counting by powers of 2 from the from the right to the left. And then on the side there, you'll see the binary. In each of these zeros and ones, those are the actual bits that are used to make up that character set. And maybe we'll have time we'll even do a calculation. But with ChartPad, it already does that for you. But back in the old school days, you actually had to do this yourself, as you can see this example on actual graph paper. Imagine those supplies. So this is a character set AXI example. The screen itself, when you turn on the display, by the way, you're looking at the Commodore 64 screen or in Vice C64 where you see the ready prompt. It goes from 0 to 40 characters across and from 0 to 24 going down the screen from left to right. Occupying a total of 1,000 character positions, these are the bytes you're looking at in this example, the 8 by 8 characters. So each individual letter you type on the screen is made up of 8 by 8 with a total of 64 bits. The characters can be placed at any position on the screen. For example, in games, a lot of score panels may appear at the top of a Commodore 64 screen. And I have an example here where I'm showing a Hawkeye game, and you see at the top there's kind of a cool looking game I thought to use. And you can see there's a little scoreboard in the middle there, and there's even a little power section. So it kind of, you could move your display at the top. You can also put them on the bottom, and of course some people even put them off to the right hand side for those who don't want to work with the most significant bit. It's a way to kind of get around it. So the Commodore 64 PET AXI character set. So these little pixels can be altered once you have relocated the character ROM into your computer's memory to make a map on the screen, known as redefining a character set, or basically like with ChartPad, you can design your own little individual characters or the bits that will be used to create a tile that can be used in the actual game or project that you're implementing. This allows you to create your own world, so to speak of. Memory locations contain 2048 bytes or 2K that holds a single character set of 256 characters, made up of upper, graphical, and lowercase characters, also originally known as PETAXI, which you heard me say already. Below is an example of a typical character set. However, since the character is in ROM, it cannot be written over. To change the characters and create your own maps, the entire set has to be copied into the reserved area in RAM memory. To activate the changed characters, the bits must be switched on in register D018 or 53272. Now let's explore the multicolor character set. Multicolors can be activated using bit 4 of register 53270. Each block can contain up to 4 colors and exists as bit pairs with 4 possible values. It's important to understand also that the 2 bits side by side here will contain their own individual colors. Here's an example of each value. So as you see here, we got the 00, that's the background color. We have the 01, that's the first auxiliary color. We have the 10, that's the second auxiliary color. We have the 11, that's the foreground color. The following table here, seen here, shows what each of the 2 pairs represent and the memory registers that manage these colors. So as you look at our chart here, you can see again, I'm demonstrating to do the 2 different binary bit values, and you can see 00 is background color number 1, and that's register 53281. That's tied to it. You got 01, which is the background color number 1, and that's 53282. And you got the 10, that's background color number 2, 53283. And you got the 11, that's the lower 3 bits in color memory or color RAMs or anywhere on the actual screen that you see, the screen display. Using bit pairs creates another problem. There are now only 4 color instructions per byte instead of 8. We've doubled the number of available colors but cut in half the number of dots that can be separately controlled. The solution is that now each bit pair in a pattern controls 2 dots instead of 1. Therefore, the horizontal resolution has been cut in half. The Commodore 64 screen can occupy any of 0 to 15 colors that's on the actual color RAM area, and this color chart shows what each color will be when used. And you can see that there's colors here from 0 to 15. Now the multicolor character set actually occupies the half end of that, which is 8 to 15, which is the lowest 3 bits of color memory. And bits 0 to 2 are read as the color codes. So before we actually get into an example of showing you how the character set is initialized in assembly language, I wanted to show you at the very basics of how it would work if you were using a basic program. So I have an example here I can show you, which creates a little mini screen as well. As you can see on the screen here, I've got the character set program up here. And after we're clearing the screen, setting colors and stuff like that, and positioning stuff on the screen, which is what this line does, line 410 is actually the switching in and out of our character set, allowing the ROMs that exist, the data that exists in ROM, to be able to move it to RAM. This is why we need this setup. And then from here, the next line, well, a few lines down in 430, shows us actually switching out the data, because your character set is actually stored in ROM, so you cannot directly write over it until you copy that into the RAM area, which is exactly what's happening here on line 430. So by copying the complete character set over, we can now change letter A to a spaceship, or however it's going to work. So let's go ahead and run the program, and this is actually switching them back out here on line 450. So I'm just going to go ahead and run this program just to show you um, how it works. And there we have a character set, the example thrown up on the screen here. Just simple little graphics in this example, but just to show you what can be done when you're switching out a character set. So initially, if I go back in here and I break out here for a minute, there we go. I was like, what's going on? Okay, so anyway, switch the character. We've switched the character set back up here, and you can see that now with these were the true characters that existed before we had altered them. So this is just a simple example, and then later we'll be demonstrating this as a set in the assembly language. For this next example, I wanted you to see some of the various games that exist out there that use multicolor character graphics. Notice that each individual square will only occupy 4 colors at a time. This is because each bit pairs control 2 dots instead of 1. Each 8-bit byte still control 8 dots on the screen, but you can't split a double dot in multicolor mode. So examining these different screens here, you can see that there's many different games out there that do utilize multicolor graphics and that were very effective in it. And there's probably more than one reason that the Commodore 64 was successful at its time period than many other systems were during that era. So you can see that the Commodore 64 has an advantage, and even was even a contender for Nintendo at that time. But fortunately, things had not worked out the way they should have. But otherwise, the Commodore 64 would have remained and still probably been around today had those conflicts not taken place over inside of the actual company itself. Another thing I wanted to talk about, which would have been for the next video, but it's being combined into this video, is the display sprite data that you're seeing on the screen, or the hexadecimal display of the debugging process, which I'll demonstrate here in just a minute. This is the subroutine that actually calls it, originally was called display sprite info because it would be displaying sprite information. But initially what it's doing is it's displaying the sprite registers, and it's also displaying any of the other registers. Like you'll see, for example, here you got the map X delta and whatever you want to be able to see on the screen to see what that data is actually doing. Although much later I'll introduce you eventually to a kernel routine I came across that allows you to display direct output to the screen, and it actually saves a lot of debugging time, I found out in the process. But we'll save that maybe for another video. But anyways, what this does is it calls an area called display byte, which is reading bytes directly to the screen. And if you go over here to the screen memory area here, you'll see what it's doing is basically just reading the color data to the screen and just reading screen memory to be able to write these digits out in hexadecimal. This is the process right here that's translating it from the actual data you see on the screen to actually the hexadecimal display on the actual screen here. And this just keeps track of each digit it's writing them out. So initially here, there's a little table down here that actually creates that little output on the bottom of the screen. So I'll switch over here so you can see what I'm talking about. If you look here in this example, as you see, you'll see that we've got the collision register. So if he collides in anything, like for example, if I move over and I probably touch this pole, for example, you should see it change right there, change to 30. So it keeps track of what's being contacted on the actual screen itself, so that you can go ahead and work directly with more debugging and get rid of some problems you may be having in code and stuff like that. So that's initially all I wanted to do with that. That's why it wasn't meant to be a whole video on it. Now what I'd like to actually do is get into the project more, to kind of keep this a little bit brief and show you some of the techniques I've used, which is actually character animation, or the animation of tiles specifically in the program. So some of the examples in this video actually include swapping between 2 different character sets, which I'll demonstrate here, showing one character set of chartpad and the other character set, and just moving back and forth between them. But as you move the screen and start beginning to scroll the screen, the bits don't effectively scroll, and it kind of makes it look pretty jagged and stuff. So it's not the best, most effective way to do that, but it is something I experimented with. Also, there's the ability to animate the actual tiles directly. And what this actually involves doing is doing some bit shifting of the tiles, which I'll demonstrate here, also which was done by the program. So initially you take a tile and think of a tile itself, individual tiles in a Commodore 64 character set are actually 64 bits. And I'm actually manipulating those 64 bits and I'm shifting between them. And in the chart pad example I'm using, of course, has 4x4 tiles. So I have to go from one character to another character until I've reached all of those in that actual tile set, so to speak, before I could effectively scroll them. And that's some of the examples I like to show you here as well. Finally, we get closer to the light at the end of the tunnel and more effective animation is discovered. So in this example, I'm going to be talking about the bit scrolling technique that I came up with. Had to do some adjustment from my previous subroutines I came up with. What really puzzled me for the longest time was calculating the area between the 4x4 tiles. I did cover that briefly here, but being able to understand effectively how to scroll those pixels is what's kind of tied me up for a while. I'll switch over to one of the actual scenes that shows it running here so you can take a look at that here. So in the actual program itself, the tiles themselves are what generates what you're seeing in the scrolling technique there on the screen. So each individual area, like you see a ladder, you see a block, whatever you're seeing on the screen there, those are actually the individual tiles that make up as they're layered on top of each other. The actual technique of scrolling in this example of the bits, you can see the little pixels moving back and forth. So I'll switch back and forth here to the code again so you can take a closer look at what I'm talking about. So in the actual subroutine here, it's called water animation. If you can see that, the river animation, as I named the actual label for it, is what's reading the area found in that tile set to be able to scroll that area. And down here further, you'll see it says shift pixels right. This is where I'm starting to begin to read the screen here as I'm pointing to the table that's being pulled here from the low and the high bytes, and I'm scrolling through them with this LSAR, left shift A, basically it's just shifting the bits over to the right as you see them moving from, the left side of the screen to the right side of the screen. You could reverse them by doing, the alternative as well. Anyways, so I wanted you to see that example here, what's going on. Again, going back to the screen here, as you can see, it's effectively able to do that scrolling technique that I've been trying to accomplish. Although my real initial goal was just to try to be able to actually take a tile and then replace it with another tile that's slightly different, kind of the animation going back and forth, but I have not been able to achieve that. So to prevent the videos from going so much further from delay to YouTube, I figured I might as well show you what I'm up to, although my Facebook's been pretty good at, demonstrating that already, as you can see here. So okay, everybody, in this example, we covered a lot of different things, learning more about multicolored character graphics on your screen. I was essentially starting it out, kind of breaking down how the actual characters work in memory so you could see them actually in their actual 8x8 format of 64 pixels each, and also being able to understand how they manipulate on the screen, how they exist in the actual character set's memory, and breaking down multicolor. She understood bit pairs, being able to see that you can actually manipulate those individual bit pairs so that you could actually control various aspects within an actual picture. You can control the four colors, of course, of the multicolor, having it reduce horizontal resolution, and also being able to see, for example, how they look on actual game screens. So I showed you a few different examples of different games I utilize this. And in the actual program itself, I originally showed you how we were able to swap between two different character sets, but it affected the raster timing and the scrolling was kind of thrown off and more jagged at that point. And then eventually I came up with the only technique I could use at the time, which was scrolling the actual individual bits inside of the actual tile sets so that we could kind of achieve some kind of low form of basic animation, at least for now, for the water animation and other examples. Much later, I hope to be able to accomplish the original technique, which is to be able to swap between two individual characters without, impacting the actual rest or timing of scrolling techniques on the screen. But for now, I hope you guys enjoyed the show. Thanks for bearing with me on this long wait. I know it's been kind of a journey. I appreciate you, with your comments and everything, subscribing, ring those notification bells to get more things back into your email as quickly as possible. So, anyways, guys, thank you so much. I appreciate all your support. I do have on my Facebook, you already seen another simple subroutine. I'm sorry, a simple game going on right now for my website where I'll show you. For those who are kind of beginner level, how to create your own simple little game where you can kind of move from screen to screen instead of trying to go into more advanced stuff like scrolling and stuff like that. But anyways, thanks guys for watching. I appreciate you so much. Have a good night, good day, wherever you are.